Have you ever wondered how those massive bolts and heavy metal fittings are forged and cast? Let's find out together. The Asahi RH80 is a high-speed 2-die 3-blow cold header, engineered for precise and efficient fastener production. Thanks to its advanced 3-blow forming process, upsetting, heading, and finishing, it easily manufactures complex parts with excellent accuracy. The machine handles wire diameters up to 11 millimeters and cut-off lengths up to 65 millimeters, operating at impressive speeds of around 150 strokes per minute for maximum productivity and reliability. The CNC Control electric screw press automatic forging line represents a breakthrough in modern metal forming technology. By integrating high-precision electric screw presses, induction heating systems, and 6-axis robotic handling, the line delivers efficient, energy-saving, and fully automated production. The CNC electric screw press ensures accurate energy control, rapid stroke adjustment, and strong eccentric resistance, ideal for precision forging and sizing. Meanwhile, automated manipulators safely transfer heated workpieces between stations for consistent, high-quality results. In modern heavy industry, precision and efficiency are everything. The Skew rolling mill machine represents a breakthrough in automated metal forming technology, especially in the production of high-quality steel grinding balls. A Skew rolling mill is an advanced, fully automated system that uses 2 to 4 tilted rollers arranged at specific angles. Unlike conventional rolling methods, this machine applies a rotary deformation process. As heated steel bars are fed into the mill, the inclined rollers rotate in opposite directions, compressing and shaping the material continuously. Through this controlled deformation, the steel is gradually formed into perfectly axisymmetric components, such as 20 mm diameter grinding balls, shafts, and even tubular products. One of the most important applications of this technology is the production of grinding steel balls used in mining, cement, and thermal power plants. These industries require components with high hardness, uniform structure, and excellent wear resistance. The Skew rolling process ensures consistent dimensional accuracy and refined grain structure, resulting in superior mechanical performance. Typically, the Skew rolling mill operates as part of a complete automated production line. The process begins with automatic bar feeding, followed by induction heating to reach the required forging temperature. The heated material then enters the rolling section, where the skewed rollers form it into spherical shapes with remarkable precision. Immediately after rolling, the balls are transferred to a quenching system for heat treatment, enhancing hardness and durability. The forge, featured in this documentary, reveals a powerful blend of tradition and technology. Inside the factory, steel billets glow a brilliant orange before being shaped under massive forging presses and precision hammers. Skilled workers carefully control temperature, time, and force to ensure consistent quality. From raw material preparation to final inspection, each stage reflects discipline, experience, and dedication, preserving the authentic spirit of industrial craftsmanship. Forksevada is a prominent fastener manufacturer based in Konya, Turkey, serving key industrial sectors with high-quality screws, bolts, and other fastening solutions. Established to combine quality, reliability, and customer-centric service, the company has developed a strong reputation in both domestic and international markets. At the core of the factory is a modern production facility equipped with advanced machinery and technology. The plant handles every stage of manufacturing under one roof, starting from precise raw material selection, through forming, threading, and quality inspection, to final packaging. This integrated process ensures that each fastener meets strict industry standards and customer specifications. Fastener produces a wide range of products, including standard and special screws, bolts, and related components. With large stocks and a broad product line, the company is capable of fulfilling orders promptly while maintaining consistent quality. The factory's mission emphasizes honesty, timely delivery, innovation, and total customer satisfaction. Its vision is to be a pioneering brand in the global fasteners industry, recognized for high performance and dependable products. Today, Fastener continues to grow by investing in technology and strengthening its service to industries such as automotive, machinery, construction, and energy. The production process begins when incoming steel is delivered to the plant. Each batch is carefully inspected to ensure it meets the required mechanical and chemical specifications. Dimensions, grade, and heat numbers are verified and recorded. After approval, the material is labeled and transferred to the new storage facilities, where it is systematically organized for traceability and efficient retrieval for production. When an order is released, steel bars or wire rods are transported to the automatic forging line. The material is first cut into precise lengths suitable for bolt formation. These cut blanks are then fed into the forging machine. During the initial stage, diameter reduction is performed to achieve the required shank dimensions. The material is plastically deformed under high pressure, forming the bolt head and shaping the body in a continuous, automated sequence. Each stroke of the forging press ensures consistent geometry and dimensional accuracy. After forging, the semi-finished bolts proceed to thread forming. In the thread rolling stage, the threads are created by cold forming rather than cutting. The bolt blank passes between hardened rolling dies, which gradually press the thread profile into the surface. This method improves surface finish and increases strength due to work hardening. For certain specifications, turning of the thread diameter is carried out before the final thread rolling operation to guarantee precise tolerances and optimal thread geometry. A second thread rolling process may follow to refine the profile and ensure full compliance with dimensional standards. Once the mechanical shaping is complete, the bolts undergo heat treatment. Hardening of the bolts is performed in controlled furnaces, where they are heated to a specific temperature and then quenched. This process alters the internal microstructure, increasing strength and durability. Tempering follows to achieve the required balance between hardness and toughness. The heat treatment cycle is closely monitored to ensure uniform mechanical properties throughout each batch. After heat treatment, the bolts move to surface treatment. Cleaning processes remove scale and residues before protective coating is applied. Zinc coating is deposited to provide corrosion resistance. The zinc thickness is tested at timed intervals to verify compliance with specified requirements. Measurements are taken not only on the bolt body but also including the thread, ensuring full coverage and consistent protection across all functional surfaces. Quality control is integrated throughout the entire process. Hardness tests are performed to confirm that heat treatment has achieved the required values. Tensile strength tests are conducted to measure the maximum load the bolts can withstand without failure. In addition, friction tests according to EN 14399 are carried out for structural bolts up to size M64. These tests evaluate the relationship between torque and clamping force, ensuring reliable performance in high-strength structural applications. All inspections and tests are conducted at defined intervals to maintain strict process control. Any deviation is immediately identified and corrected to maintain consistent quality standards. After final approval, the finished bolts proceed to special packaging. They are counted, labeled, and packed according to customer requirements, ensuring protection during transport and easy identification on site. The packaged products are then prepared for shipment, completing the manufacturing cycle from raw steel to fully tested and certified bolts ready for industrial use. At the production facility of Doka Fasteners, bolt manufacturing begins on a fully automatic forging line. Steel bars are cut into precise blanks and heated before entering the new megacell, where heavy-duty presses forge bolts up to M100 or 4 inches in diameter. During forging, the head is formed and the shank is shaped under high pressure to achieve the required geometry. For certain products, diameter reduction is carried out to refine the shank dimensions before threading. Stud bolts are produced on an automatic stud line, where bars are straightened, cut, and prepared for further processing. After forming, the components undergo hardening. The bolts are heat-treated in controlled furnaces to obtain the specified mechanical properties. Once heat treatment is complete, a fully automated hot-dip galvanizing surface treatment is applied, ensuring corrosion protection and uniform coating thickness. Quality control follows strict procedures. Each batch is subjected to hardness testing and tensile strength testing to verify mechanical performance. Friction tests are performed to confirm reliable tightening behavior. Internal integrity is checked through fully automated ultrasonic testing to detect hidden cracks, while magnetic particle inspection identifies surface defects. Metallographic analysis using an optical microscope is conducted to examine the microstructure and confirm proper heat treatment. Approved products are transferred to the warehouse facilities in Norway and Denmark. According to project requirements, bolts are kitted for assembly and site delivery. The Fast Track system uses pre-made blanks and rapid thread rolling to reduce lead time. Finally, kit sets are packed based on customer needs and managed through a VMI system supported by the advanced CPS platform. This high-speed bolt manufacturing machine is designed to transform raw steel wire into finished bolts through a continuous, fully synchronized forming process. In the initial stage of the process, the steel bar is automatically fed into the machine. The bar passes through straightening rollers to eliminate bends and ensure dimensional accuracy. It then enters the cutting mechanism, where each section is precisely cut to the required workpiece length. Time is extremely critical. All movements are mechanically synchronized to maintain uninterrupted production. Next, the cut workpiece is transferred to the bolt head forming station. Here, powerful dies shape the bolt head with one or more stamping strokes, depending on the design. The force applied is carefully controlled to ensure a solid, defect-free, and precisely shaped bolt head. Immediately after head formation, the partially formed bolt is transferred to the threading unit. Using flat or cylindrical dies, threads are rolled onto the bolt body instead of being cut. This rolling process increases strength by maintaining the grain orientation of the material while creating smooth and precise threads. Throughout the machine, cams, stamping, and drive mechanisms work in perfect coordination. The system operates continuously, producing a consistent and stable flow of bolts at a considerable speed. Finished bolts are automatically ejected and collected for heat treatment or surface finishing if needed. Automated bolt production machines demonstrate how automation, mechanical timing, and powerful forming technology combine to achieve high productivity and consistent quality. They are essential equipment in industries such as construction, automotive manufacturing, and heavy machinery assembly, where robust and reliable fasteners are required. After the billet has undergone preliminary shaping in the initial press, the roughly formed hot blank is immediately transferred to the final forging machine while it is still at a high temperature. Maintaining heat at this stage is essential to ensure the metal remains plastic and capable of flowing accurately inside the die cavity. The red-hot preform piece is carefully positioned between the upper and lower closed dies of the forging press. These dies are precisely machined to match the exact geometry of the finished mechanical component. Once the billet is correctly aligned, the operator activates the large industrial forging press. With a powerful downward stroke, the upper die compresses the heated metal. Under intense pressure, the material flows outward and fills every contour of the die cavity. The internal grain structure is further compacted and aligned along the shape of the part, improving mechanical strength. Excess material is forced into the flash gap around the die edges, ensuring complete filling of the mold. After the forging stroke is completed, the press retracts and the newly formed component is removed using handling tools. The hot forged part is then transferred to the trimming stage, where excess flash will be cut away in preparation for subsequent finishing operations. The FP800G aluminum forging press is a high-performance hydraulic forging machine engineered for precision and strength. Designed specifically for aluminum alloy forging, this press delivers a powerful and stable forming force, enabling the production of dense, high-integrity components with excellent mechanical properties. With its robust frame structure and advanced hydraulic control system, the FP800G ensures consistent pressure distribution throughout the forging stroke. This allows aluminum billets to be formed efficiently into complex shapes while maintaining dimensional accuracy and surface quality. The machine is equipped with an automated control interface that enhances operational efficiency, reduces manual intervention, and improves production safety. The FP800G is widely applied in industries such as automotive, aerospace, and industrial machinery, where lightweight yet high-strength aluminum components are essential. By combining high-tonnage capacity with precise control, this forging press represents a reliable solution for modern aluminum forging production lines. Brass scraps and discarded metal components are first collected and charged into a melting furnace. Inside the furnace, the brass is heated until it becomes fully molten. At the same time, an induction billet heating furnace is used to ensure the metal material is heated evenly and reaches the required temperature for further processing. Once the brass has completely melted, the worker carefully pours the molten metal into molds to form solid billets. These newly formed brass billets, still glowing with heat, are then removed from the mold for the next stage. The hot billet is transferred directly to the extrusion machine. The operator inserts the heated billet into the extrusion chamber, where powerful pressure forces the brass through a shaped die. As a result, long, red-hot brass strips emerge continuously from the machine. These extruded sections carry the basic profile required for hinge production. After extrusion, the long brass strips are allowed to cool slightly and are then cut to remove excess material and uneven ends. The trimmed sections are inspected to ensure uniform dimensions. Next, the semi-finished brass bars move to the grinding and machining stage. During this process, workers refine the surface, smooth rough edges, and shape the profile more precisely to meet hinge specifications. Finally, the machined brass strips are cut into individual hinge pieces of the required size. Each piece is separated cleanly, completing the transformation from recycled brass scrap into finished brass hinge components ready for further assembly or finishing operations. The production process of brass fittings begins with 3D modeling based on client drawings, enabling close collaboration during component design. A prototype is then developed and tested for functional accuracy. The mold is designed using CAD/CAM to generate CNC tool paths. Brass bars from certified suppliers are cut precisely using PLC-controlled systems. Hot forging is performed using 20 advanced presses to shape the parts. Afterward, sandblasting removes residues and enhances surface quality. CNC turning follows, with roughing and finishing to achieve precise dimensions and tolerances. Finally, high-efficiency transfer machines complete the process, ensuring maximum productivity and customization. The production of valves and water meters at Clepson Valve and Water Meters begins with a strong data foundation and proceeds through carefully controlled industrial stages. Established in the 1970s with valve couplings and check valves, the company now manufactures more than 350 product types for hygienic installations, natural gas systems, agricultural irrigation, and measurement tools within a 15,000 square meter closed facility equipped with advanced machinery. The process starts in the foundry, where approximately 5,000 tons of MS-58 brass are melted annually. The molten metal is transferred to the molding house, followed by press forming using fully automatic forging and beating presses capable of producing up to 100,000 units daily. After forming, components move to precision machining, ensuring exact dimensions and surface quality. Next, parts pass through coating operations for corrosion resistance before entering the assembly and plastic injection units. Automated assembly lines connected to integrated control systems guarantee consistent quality without compromise. In addition to valves, the factory produces over 500,000 water meters annually. Supported by specialized engineers and R&D experts, the company designs its own molds and technologies, delivering fully domestic production with internationally certified standards and a global marketing network. The production process at Hydropont begins with the preparation of raw steel billets. Large steel bars are first cut to the required length using gas cutting equipment. For higher precision and cleaner edges, plasma cutting of billets is also applied, ensuring uniform dimensions before forging. These prepared billets are then transferred to the respective technological lines depending on the final product and required size. On the processing line for forging steel balls with diameters ranging from 60 mm to 120 mm, the billets are subjected to inductive heating. The induction furnaces raise the temperature of the steel rapidly and uniformly to forging temperature, ensuring optimal plasticity. Once heated, the billets move directly to the forging units. Steel balls of 100 mm and 120 mm are forged on heavy-duty forging presses designed to withstand high forming forces. For smaller sizes from 60 mm to 90 mm, a separate forging section operates with equipment optimized for these dimensions. Each billet is shaped into a spherical form through controlled deformation under high pressure. Immediately after forging, the red-hot steel balls are discharged into a water-quenching tank. This rapid cooling process increases hardness and improves wear resistance, which is essential for grinding applications. The quenching parameters are carefully controlled to ensure consistent metallurgical properties throughout the batch. After cooling, the balls are inspected and transferred to the packing section, where they are sorted, weighed, and packed for shipment. For the production of 40 mm steel balls, a dedicated technological line is used. Steel bars are placed in a magazine for automatic feeding, which ensures continuous and stable supply to the line. The bars pass through an inductive heating installation manufactured by BBS Brown Boveri, where they are heated to the required forging temperature. Once heated, the bars are cut into precise lengths by a hydraulic press shear produced by FICEP. This step guarantees accurate billet dimensions before forming. The cut billets are then transported to the forging stage. For heavy forged products, such as steel shell casings weighing up to 50 kilograms, a hydraulic press from EUMUCO performs the primary forming operation. The heated billets are compressed and shaped under controlled pressure. Additional forming operations are carried out in a unit equipped for compression, push broaching, and drop hammer traverse. These processes refine the geometry and ensure the required structural integrity. After primary forging, the shell casings undergo calibration in a drawing unit fitted with rolls and rings. This stage corrects dimensional deviations and improves surface quality. The hot forged shell casings are then arranged onto pallets by a robotized stacker. The automated system ensures safe handling of high-temperature components and organizes them into arrays for subsequent normalization heat treatment. Normalization refines the grain structure and enhances mechanical properties. The factory also operates a dedicated line for mechanical processing of shell casings. Forged components are first loaded into an automated magazine for billet charging, which feeds them sequentially to the machining stations. Prior to machining, components may be reheated using an inductive heating unit manufactured by EMA to facilitate forming corrections or bending operations. Turning operations are performed on high-efficiency programmable lathes. A GF hydrocopying lathe carries out the external turning of the shell casings with high precision and productivity. For final internal machining, the final 130:1 programmable lathe performs the finishing turning of the inner surfaces, ensuring dimensional accuracy and surface smoothness according to technical specifications. For specific forming requirements, shell casings are processed on a vibrating forging press manufactured by Usain de Wecker. This equipment is used for bending operations and controlled deformation, improving the final geometry and mechanical characteristics. Throughout the forging and machining stages, two manipulators assist in handling heavy components, transferring them safely between stations, and ensuring stable positioning during processing. In addition to steel balls and shell casings, the forging facilities are capable of producing various other forged products with individual weights reaching up to 40 kilograms. The combination of inductive heating systems, hydraulic presses, calibration units, and automated handling equipment enables efficient large-scale production while maintaining strict quality standards. Each stage, from billet preparation and heating to forging, heat treatment, machining, and packing, is integrated into a continuous technological flow, ensuring high productivity and consistent product performance. In the closed die forging process for an eye bolt, a steel billet is first heated to a high temperature until it becomes plastic and workable. Once the required forging temperature is reached, the hot metal is placed between two forming dies and pressed firmly to create a rough preform of the product. This initial pressing operation gives the billet a basic shape and prepares it for further forging steps. Next, the roughly shaped workpiece is transferred to a forging hammer. The hammer delivers repeated powerful blows onto the hot steel, consolidating the material and refining the preliminary shape. These impacts improve the internal structure of the metal and bring it closer to the final geometry. After hammer forging, the part is moved to a closed die forging machine. Here, it is forged again, inside precisely machined dies that form the accurate shape of the eye bolt, including the eye section and shank. Excess flash material that flows out along the die parting line is then trimmed off using a cutting or trimming machine. While the workpiece is still red hot, it is briefly quenched in water and then forged once or twice more in the closed die to enhance dimensional accuracy. Finally, the eye bolt undergoes grinding to achieve its exact shape and a smooth, finished surface. The induction brazing process is a precise, high-speed, and repeatable non-contact method used to join metallic components. Unlike traditional torch or furnace brazing, this technique uses an electromagnetic field to generate heat directly inside the metal parts. The parts are heated to a temperature above the melting point of the filler metal, but below the melting point of the base materials. As a result, the filler alloy melts, flows into the joint, and forms a strong metallurgical bond without melting the main components. At the heart of the process is electromagnetic induction. An induction generator, also known as the power supply, delivers high-frequency alternating current to an induction coil. When energized, the coil produces an alternating electromagnetic field around it. If a conductive metal part is placed within this field, electrical currents known as eddy currents are induced directly inside the workpiece. Due to the electrical resistance of the material, these currents generate heat rapidly and locally within the metal itself. This localized heating is one of the defining characteristics of induction brazing. Only the area near the joint is heated, while surrounding regions remain relatively cool. This minimizes thermal distortion, protects heat-sensitive components, and reduces overall energy consumption. Because the heat is generated internally within the workpiece rather than applied externally, the process is both fast and highly efficient. Before heating begins, the joint area is prepared and the filler metal is positioned. The filler material is commonly supplied in the form of paste, wire, or preformed rings. Silver-based or copper-based filler alloys are typically used due to their excellent flow characteristics and strong bonding properties. As the induction coil heats the base metals to the required temperature, the filler metal melts. Through capillary action, the molten filler flows into the joint gap, filling it completely and creating a uniform bond upon cooling. A typical induction brazing system consists of three main components. The first is the induction generator, which controls power output, frequency, and heating time. The second is the induction coil, carefully designed to match the geometry of the parts being joined. Coil design is critical because it determines heating efficiency and uniformity. The third component is often a cooling unit, or chiller, which maintains stable operating temperatures for the generator and coil during continuous production. One of the most important advantages of induction brazing is its high repeatability. Because power, frequency, and heating time can be precisely controlled and programmed, each cycle produces consistent and identical results. This level of control ensures reliable joint quality, which is essential in industries requiring strict performance standards. Speed is another major benefit. Brazing cycles are often completed in just a few seconds, making the process ideal for high-volume manufacturing. The rapid heating and cooling reduce overall production time while maintaining excellent joint integrity. Cleanliness also distinguishes induction brazing from flame-based methods. Since there is no open flame or combustion, there is no soot or direct flame contact with the parts. Oxidation is reduced, and the need for extensive post-braze cleaning is minimized. This contributes to a safer and more environmentally friendly working environment. Furthermore, induction brazing integrates easily into automated production lines. Systems can be combined with indexing tables, carousels, or robotic handling units to create fully automated assembly operations. The non-contact nature of the heating process enhances reliability and reduces mechanical wear. In addition, the process is energy efficient. Because heating is localized and targeted, energy waste is significantly lower compared to torch or furnace brazing methods that heat large areas unnecessarily. Overall, induction brazing provides a fast, clean, energy efficient, and highly controllable joining solution. By combining electromagnetic heating with precise system control, it ensures consistent quality and seamless integration into modern automated manufacturing environments.